All right, example 2. Find the percent error for Taylor's measurement 1. What does this mean? So we're going to go back and look at Taylor's measurement 1. And we're going to look at this part right here that we used. This was our, if we think back to our formula, our a minus x. So this was the top part of that fraction. So we're going to have 15 and 2/8 minus 15 in our absolute value brackets, all divided by the actual measurement times 100%. Okay, so now to work this, we're going to subtract out, which we already found this top part. In our first example, we found that it was equal to 1/4 of an inch. So 1/4 over 15 times 100. To divide fractions, we keep, change, flip. So 1/4 times 1 over 15 times 100. I'm going to make that into a fraction. So we can multiply 1 times 100 is 100. 4 times 15 times 1 is 60. When we simplify this, 1 40/60, which simplifies to 1 2/3%. So this means Taylor's measurement of 15 2/8 has a percent error of 1 2/3%. All right, let's look at our next part of this question. It says, from example 1, part B, find the percent error for Connor's measurement 1, and what does this mean? So if we look back at Connor's measurement 1, here's the first part of our work. So his measurement minus the original, and then we found that to be 1/2 of an inch. So let's see what that looks like. So Connor's measurement of 15 4/8 minus the original value, or what it actually is, all over the actual exact value times 100%. All right, so we know from our previous work that the 15 4/8 minus 15 is 1/2, so we have 1/2 divided by 15 times 100%. To divide our fractions, we are going to keep, change, flip. 1/2 times 15 over 1 times 100 over 1. Oops, sorry, I didn't flip this. Let's try that again. 1 over 15. So now we can multiply 1 times 100 is 100. 2 times 15 times 1 is 30. When we simplify this, we get 3 10/30, which is 3 1/3%. So this means Connor's measurement of 15 4/8 of an inch has a 3 1/3% error. So if we look at his error compared to what Taylor's error was, Taylor's error is smaller, which means her measurement was actually closer to the actual exact value, where Connor's measurement was further away. All right, we have one more example on this one to look at, and that is looking at Jordan's measurement 2. So if we take our previous work and apply that to our formula, 14 6/8 minus 15 all over the actual measurement times 100%. All right, so we know from our problem that it was 1/4. So 1/4 divided by 15 times 100. So again, to divide our fractions, keep, change, flip. See if I remember to flip it this time. 1/4 times 1 over 15 times 100 over 1. 1 times 1 times 100 is 100. 4 times 15 times 1 is 60, which is 1 40/60, which when we simplify is 1 2/3%. So this means Jordan's measurement of 14 6/8 of an inch has a 1 2/3% error. So you might be thinking to yourself, why do we find our percent error? Why is this an important thing? Well, when we find our percent error, it allows us to actually compare things with taking into consideration the units that we're talking about. So let's put down, it tells you how big your error is, how big your error is compared to the actual value. Now you might still be asking, but why is that important? I want you to think about this. Might be good to write it down so you can look at it later. So think about this. An error of 1 centimeter is small when we're talking about measuring for marathons. We're talking about, what, 32 plus miles. Is small if we are measuring, yes, you are measuring for a marathon. But 1 centimeter is large for an error if you were a heart surgeon working on a tiny heart. So if you are a heart surgeon, working on a small heart. So by finding the percent of that error, it helps us determine takes it all out of the same number to know whether it's something small or whether it's something really big.